Today we shall study normal distribution. It's a very important distribution as far as the statistical analysis is concerned and also the inferential problems are concerned. But before going into normal distribution, we need to understand some prerequisites. So we start with a random variable. What is a random variable? Given a sample space omega, a random variable is defined as a function on omega into the real line. Very difficult to understand. Let us take one or two examples to clarify this idea. So we have to remember two things, that this is a function on the sample space and into the real line. So let us try to understand what do you mean by this definition. So we take the first example, we toss a coin thrice. That means how many outcomes will be there? There will be in all 8 outcomes. How do we enumerate these outcomes? First, when we toss a coin 3 times, what is the maximum possible number of heads? 3. So H will be 1 outcome. Next possible number of heads is 2. So how many outcomes are possible with these 2 heads? HHT, HTH and THH. Next possible number of heads is 1. With 1 head, what are the possible outcomes? HTT, THT and TTH. And finally, we may not have any head at all, so TTT. So how many total number of outcomes are there when we toss a coin thrice? 8 outcomes. Now see, if I define a random variable x as, okay, forget about a random variable. First think about a variable. We define a variable x as number of heads obtained in 3 tosses. Now, when the outcome is HHH, what will be the value of x? 3, because there are 3 heads. When the outcomes are HHT or HTH or TTH, what will be the value of x? X will be equal to 2. So, x will be equal to 2 for 3 outcomes. Similarly, x will be equal to 1 when the outcomes are HTT or THT or TTH. Finally, x will take up the value 0 for the outcome TTT. So we can see the variable x can take up the values 0, 1, 2 and 3. So you see it takes up the values depending on the outcome in the sample space. So we come back to the definition that it is a function defined on the sample space. Now what are the values of x? Here in this particular example, these are 0, 1, 2 and 3. So all of these real numbers. So it's a function into the real line. Now I hope the definition is more or less clear. Random variable is a function on omega into the real line. Now why it is called a random variable, not an ordinary variable? Okay, we take one more example and then we shall come back to this point. Our next example is roll a die once. So we know the outcomes are 1, 2, 3, 4, 5, 6. Now if you can recall, we defined a random variable as a function. So I can write xe equals to e minus 3, because any function, say fx, we can write it as x minus 3. So in particular here we are defining xe equals to e minus 3, where e will be the outcomes in the sample space. So when e is 1, it is very much clear that x will have the value 1 minus 3, that is minus 2. Similarly, for x equals to 2, 3, 4, 5 and 6, the values of x will be minus 1, 0, 1, 2 and 3. So here also x takes several values and these values will depend on the outcome of the random experiment. Now the question of randomness. Let us try to address this question. Now see, when x takes up the value minus 2 here, when x takes up the value minus 2, when the outcome is 1. Now what is the chance or the probability of this outcome? 1 by 6, given that the coin is unbiased. So as 1 has the probability 1 by 6, similarly the probability that x will take up the value minus 2 is 1 by 6. In the previous example, in example number 1, if I ask you what is the value of x, what is the probability that x will take up the value 2, will you be able to answer? Now see, x takes up the value 2 for which outcomes? For 3 outcomes. How many outcomes are there in all? 8. So if you go by the classical definition of probability that x equals to 2 will be 3 by 8, right? So you see here also the variable x assumes different values with different probabilities, and that is why we say this variable to be a random variable. Just keep in mind that a random variable can take up different values with different probabilities. That will lead us to our next concept, which is called the probability distribution of a random variable. Now, as a normal variable, a random variable may be of two types, discrete and continuous. What is a discrete random variable? A random variable that can assume either a finite number of values or countably infinite number of values. Now, what do we mean by these two? Let me explain these two terms properly. Finite number of values we can all understand. The last two examples that we have taken up, in the first example, x took 8 values, or to be specific 4 values with different probabilities, and in the second example, x took 6 values, right? So we had finite number of values. Now what can be countably infinite number of values? You see, let me give you an example. Suppose the random experiment is tossing of a coin until a head appears. Let me explain what do we mean by this example. So we'll first toss a coin. If I get a head, I'll stop. Suppose I do not get a head in the first toss. Then I'll toss it again. I get a head in the second toss. So I stop there. That means in the first toss I get a tail, and in the second toss a head. What are the other possibilities? It may be that in first two tosses I do not get a head, tail and tail, and in the third toss I get a head. So I stop there. So this process is continued. Now it is not ensured that we'll get a head definitely at some point of time. So what will be the sample space? H, TH, TTH, TTTH, and it will go on like this. So it will be an infinite sample space. Now if I define x as number of tosses required to get the first head. Number of tosses required to get the first head. Now you see, when the outcome is h, what is the value of x? 1. When the outcome is th, 2 tosses are required, so x will take up the value 2. When the outcome is tth, then 3 tosses are performed, so x will take up the value 3, and so on. So that means it will take up an infinite number of values, because 1, 2, 3, 4 like this. But it's countably infinite. Unlike a continuous random variable, which will take up uncountably infinite number of values, which we shall take up a bit later. So first we will discuss the probability distribution of a discrete random variable. So x is a discrete random variable that can take up either a finite number of values, we can call them x1, x2, xn, and also countably infinite number of values, which we denote by x1, x2, etc. dot dot dot. And we have seen that a random variable takes up values with corresponding probabilities. So the probabilities will be p1, p2, pn in the finite situation, or p1, p2 dot 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 in the infinite situation. Obviously, the total probability will be equal to 1. So we can, for any particular example, we can form a table where x will take up the values with the corresponding probabilities. A tabular form or specification of this is called the probability distribution of a discrete random variable. So this is the first example. Toss an unbiased coin twice. So the sample space is h, h, t, th, tt. We are defining x like the beginning, that x is the number of heads obtained in 2 tosses. So clearly for the outcome hh, x will take up the value 2. For the outcomes ht and th, x will take up the value 1. And for tt, x will take up the value 0. So that means x takes up the values 0, 1 and 2. Let us see carefully. Probability x equals to 0. First you imagine when x takes up the value 0. When x takes up the value 0, when the outcome is tt. What is the probability of getting this outcome tt? 1 by 4. So probability x is equal to 0 will be 1 by 4. Similarly, probability x is equal to 1. Now the outcomes favorable to x equals to 1 are ht and th. So probability x is equal to 1 will be simply 2 by 4, that is half. In the same way, you can easily find out that probability x is equal to 2 will be again 1 by 4. As you can see on the screen, we can have these values along with the probabilities in a table. And obviously the total probability will be equal to 1. Now, if you look at the screen, we have written small x, and in the next row, probability capital X is equal to small x. Now, small x will denote the value of the random variable, while capital X will denote the random variable itself. Remember, we always denote random variables with uppercase letters, capital X, capital Y, capital Z, etc., and their values with the corresponding lowercase letters. So, when we talk of a discrete random variable, the question of a continuous random variable comes up. As I hinted earlier, a continuous random variable is such a random variable which can take up uncountably infinite number of values within its range of variation. Suppose we measure the height of a randomly selected person from a group, or we can take up the weight as well, we can take up something else as well, like diameter, volume, density, so on and so forth. Okay, let us stick to the weight of a randomly selected person. Suppose in that group, everybody has weight between 60 kg and say 120 kg. Everybody has got weight between 60 kg and 120 kg. So it's clear that X will take up a value between 60 and 120. That is obvious. I'm telling you one value, 61. Will you be able to tell me the next value? No. If you tell me it is 61.1, then I'll say it may be 61.01. If somebody tells me it is 61.01, I'll say 61.001. That is also next possible value. That means we can appreciate one fact, that given a particular value, we are not being able to tell what will be the next value. Unlike the previous example of a discrete random variable, if the number of tosses required is 5, this is given to me, and I am asked that what will be the next possible value, I will unambiguously say that the next possible value is 6. So, there are difference between the two infinities. In the coin tossing situation, the number of values is infinite, but we can say what is the next value. But in this situation, in the case of weight, the number of values is infinite, but we are not being able to say what is the next value. So in the earlier case, it was countably infinite, and now it is uncountably infinite. So a continuous random variable can take uncountably infinite number of values within its range of variation. Next topic that we will go into is cumulative distribution function. It is a very important topic. Probability capital X less than equal to small x. It is called cumulative distribution function, and we denote it by capital Fx, where the values of x are real numbers. Now, can you tell me what does this physically mean in terms of a probability distribution? So let us come back to the cumulative distribution function. So what does it physically mean? It is basically the area to the left of a value. Probability capital X less than equal to small x. So it is basically the area to the left of the value small x. Now there are certain properties of a cumulative distribution function. These properties are necessary and sufficient. I'll explain what do we mean by necessary and what do we mean by sufficient. But let us look at the properties first. F has to be a monotonically non-decreasing function. That is, for all x1 less than x2, fx1 has to be less than or equal to fx2. Next, f of minus infinity is 0. Number 3, f infinity is equal to 1. And fx, number 4, has to be right continuous everywhere. That means, limit epsilon tends to 0 plus, fx plus epsilon has to be equal to fx. Now, these 4 conditions are very important, and we have to remember these 4 conditions. These conditions are necessary as well as sufficient. What do you mean by the conditions are necessary? That means if a function fx is a distribution function or a cumulative distribution function, then it must possess these 4 properties, right? On the other hand, the conditions are sufficient. So what do we mean by this sufficiency? If a function f satisfies these 4 conditions, we can say that the function is a cumulative distribution function. So in this sense, these conditions are necessary as well as sufficient. Now we come to something called probability density function. Suppose x is an absolutely continuous random variable. Then we can have a non-negative integrable function small f such that you can see on the slide capital Fx is integration from minus infinity to x small ft dt. This function small f is called the probability density function of the random variable x. There are some important notes. F is called the probability density function, as we have said. Now fx must satisfy two properties. That is, fx has to be non-negative for all possible values of x, and integration from minus infinity to infinity fx dx should be equal to 1. Now again you can see, for any a strictly less than b, suppose I want to find out the probability that x lies between a and b. So x lies between a and b, so probability x less than equal to b minus probability x less than equal to a. X less than equal to b means what? The area from minus infinity to b, and x less than equal to a means area from minus infinity to a. So probability x less than equal to b minus probability x less than equal to a, that means basically the area between a and b. So by the definition of cumulative distribution function, as we have seen earlier, we can write this as fb minus fa. Now you put the formula, fb is minus infinity to b fx dx, and capital Fa is integration from minus infinity to a fx dx. So basically it comes out to be probability integration from a to b fx dx. So probability that x lies between a and b is nothing but the integration of the PDF from a to b. This is how we work it out mathematically. Now we come to the normal distribution. Normal distribution is the distribution of a continuous random variable. And a continuous random variable x is said to follow a normal distribution if its PDF is given in the form as you can see on the screen. Fx is 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square, where x lies between minus infinity and infinity. Now you can see, apart from x, there are three constants. One is sigma, one is pi, and the other one is mu. Now pi is our normal pi, which is 3.14, that we know. Mu and sigma are the two constants which characterize this distribution. That means if you change the values of mu and sigma, the distribution will get changed in terms of the probabilities. So mu and sigma are called the parameters of the distribution, and for the normal distribution it is known that mu lies between minus infinity and infinity, while sigma lies between 0 and infinity. Now whenever we say that x follows a normal distribution, we won't say it in words always, we fix a notation. So notation is x follows normal mu sigma or x follows normal mu sigma square. We can use either of the two notations. In the references given, you can find the various books. Various books will give you various notations. So let us be familiar with both the notations. There are certain important properties of a normal distribution. Obviously, for any probability distribution like frequency distribution, mean, variance, skewness, these are the important properties. So the first property is expectation of x is equal to mu. That means the constant mu that we talked about is nothing but the mean of the distribution. And variance of x is sigma square. Variance of x is sigma square means the constant sigma we talked of is nothing but the standard deviation of the distribution. You can see a normal curve on your screen. A normal curve is a bell-shaped symmetric curve. You can see it's symmetric on both sides. That means the two tails are similar. As we move towards the positive or the negative direction of the x-axis, the tails are similar. These type of distributions are known as symmetric distribution, and in particular a normal distribution is a symmetric distribution, and it's a bell-shaped distribution, you can see from the diagram. So we carry on with the properties. A normal distribution is asymptotic to the x-axis. What do you mean by this? That means as we move towards the positive or the negative direction of the x-axis, the curve will come closer and closer to the x-axis but will never meet it. This is called asymptotes. Now see, that means if it does not ever meet the x-axis, that means fx cannot be equal to 0. You can look it from the functional form of the PDF as well. It is 1 by sigma root 2 pi e to the power minus half x minus mu by sigma whole square. We know e to the power anything is strictly positive, and the rest constant 1 by sigma root 2 pi. Sigma by definition is positive, root 2 pi is definitely positive. So fx is always positive. Fx cannot ever be equal to 0. So that is why the curve is asymptotic to the x-axis. It never meets it. Another very important property is this. If y is a linear function of x and x follows a normal distribution, then y will follow a normal distribution as well. So suppose x is a random variable that follows a normal mu sigma square distribution, that is a normal distribution with mean mu and variance sigma square, and y is equal to a plus bx, that is a linear function of x where a and b are constants. Then we can show that y follows a normal distribution with mean a plus b mu and variance b square sigma square. Now we come to a very important topic which is called standard normal variate or normal deviate. Suppose x follows a normal distribution with mean mu and variance sigma square. We define z which is equal to x minus mu by sigma. Can we very quickly say what is the mean and variance of z? Mean of z means expectation of z. Z is x minus mu by sigma. So expectation of z will be ex, that is expectation of x minus mu by sigma. We know expectation of x is mu, so it is mu minus mu by sigma, so 0. So z will have the mean 0. What is the variance of z? Again, z is x minus mu by sigma. So variance of z will be 1 by sigma square into variance of x. Variance of x is sigma square, we know. So variance of z will be sigma square. That means z will have the mean 0 and variance 1. And by the earlier property, you can see that z is a linear function of x. So z will also follow a normal distribution. So the distribution of z will be normal 0, 1. Now, for any random variable, as we have probability density function, cumulative density function, similarly for z, we will have PDF and CDF. We already defined what is a PDF, what is a CDF. Can you be able to tell us what will be the PDF of z and the CDF of z from the definition that we have done earlier? So the PDF of z is very simple. It's basically the PDF of a normal distribution with mean 0 and variance 1. You can see on the slide. The CDF can also be seen on the slide. One good thing is this: the values of capital phi z, that is the CDF of z, are tabulated in biometric tables and also in various statistical softwares. So we need not perform this integration actually. Area properties. For any k, suppose I want to find out probability x less than equal to k. That can easily be found out in terms of capital phi, the CDF, as capital phi of k minus mu by sigma. Similarly, for any a less than b, if we try to find out probability that x lies between a and b, that can also be found out in terms of capital phi as capital phi of b minus mu by sigma minus capital phi of a minus mu by sigma. Given the values of a, b, mu, sigma, etc., we can find out the value of capital phi from the table or from the software. So it's very easy to calculate. And there is a very interesting property that for any k greater than 0, capital phi of minus k can be obtained as 1 minus capital phi of k. Effective range. We have seen from the PDF that a normal distribution varies between minus infinity and infinity. But for all practical purposes, it may be assumed that the random variable lies between mu minus 3 sigma to mu plus 3 sigma. Why? Because the probability that x will lie between mu minus 3 sigma and mu plus 3 sigma is very high. On the other hand, the probability that it will lie outside this interval is negligibly small, which is 0.0027. What does it mean? At random, if I select 10,000 values from a standard normal variate, then only 27 of them will fall outside the range. That means most of the values will fall within this range. This is why the interval mu minus 3 sigma to mu plus 3 sigma is often referred to as the effective range of the normal distribution. Now, why are we studying normal distribution? Why it is useful? Actually, many natural phenomena are normally distributed. Height, weight, IQ, intelligence, everything, these are normally distributed. So that is why normal distribution is very important, because it resembles the real life situation. The normal distribution is very easy to work with. That is, it lends itself to various mathematical properties, so the computation becomes very easy. Also, there is a very strong connection between the sample size and the normal distribution. As we go on increasing the sample size, we can find that many sample characteristics will follow a normal distribution. So this is why normal distribution is so useful in statistical analysis. Now, what is the importance of normal distribution? The importance of normal distribution primarily lies in the fact of central limit theorem. What is the central limit theorem? That means when the sample size is large enough, then the sample characteristics will follow a normal distribution around the corresponding population characteristics. Follow a normal distribution, I repeat. So this is why central limit theorem is very important, and for central limit theorem we need normality, normal distribution. So we need to know the characteristic properties of a normal distribution. If a random variable x follows a normal distribution, then the probabilities are very easy to compute, very easy to calculate. Normal distribution has got wide range of application as well. One application I can give an example right now is in statistical quality control, where we use 3 sigma limits. Let me tell you in a very brief manner, without going into the details. Suppose there is a process going on, suppose chalks are being prepared in a particular machine. Now obviously it's not possible that all chalks will have the same length. Some chalks will be longer, some will be shorter. Now in process control, there is a technique which is called control charts, which says that if the length lies between mu minus 3 sigma and mu plus 3 sigma, then the product, the article, the chalk in this case, will be considered to be acceptable, that is non-defective. Otherwise, it will be considered to be defective. Now, you match this idea with the effective range. In case of effective range, we said the probability that x will lie between this mu minus 3 sigma to mu plus 3 sigma range is 0.9973, which is almost 1. And we are doing the same thing in statistical quality control. And the whole theory of testing of hypothesis, we will come later in later courses. T-test, F-test, chi-square test, they all assume normality. They all assume normal distribution. We can take some real-life examples. Suppose we are interested in the heights. Now, if we collect the height of many individuals, you can find that the heights are normally distributed. More the individuals, more the shape will be revealed. If you roll a fair die quite a number of times, now mind you, at each throw, there will be 6 outcomes will appear in any throw. Now, if you throw the die many number of times, there will be some number of times in which 1 will appear. There will be some number of times in which 2 will appear, and so on. So we can construct a frequency distribution of that type. When we consider the frequency distribution and the corresponding histogram, we can see that the histogram will look like a normal distribution, histogram of a normal distribution, provided that the number of throws is large enough. You can see now in various advertisements of schools, colleges, institutes, etc., they are talking of intelligence, they are talking of IQ. This IQ, intelligence, is also normally distributed. That means if we take a very large number of individuals and measure their IQ and want to plot it graphically, we can see that they are normally distributed. So this is why normal distribution is very, very important in our course of study. And in our next course of study, when we will take up sampling distribution, chi-square test, t-test, f-test, etc., we can more appreciate how normal distribution is important. Now we come to some applications of normal distribution. Suppose x follows a normal distribution with mean 12 and standard deviation 4. Suppose we have to find out probability x greater than 20. And the value of phi 2 is given. As I mentioned, that these are available from the table. So mu is 12, mean is given to be 12, standard deviation 4. So sigma is 4. So we can find out probability x greater than 20 as 1 minus probability x less than or equal to 20. And by the area property of the normal distribution, it will be 1 minus capital phi of 20 minus mu by sigma. Mind you, mu is 12 and sigma is 4. So that basically comes out to be capital phi of 2. 1 minus capital phi of 2, value of phi 2 is given. So we can easily compute 1 minus capital phi of 2. So now you can see how easily we can find out a probability. In the next example also, we can find out the probability in a very easy manner. We know that family income follows a normal distribution with mean $25,000 and standard deviation something. So we have to find out the percentage of the population that will benefit from the law. So we'll again use normal distribution, and we can again find out that this proportion in terms of the probability is 2 of capital phi into 0.5, which comes out to be 0.383. So you can see that normal distribution is very easy to deal with, and we can find out later on that it has got immense importance in various statistical techniques. So we will go on studying normal distribution more effectively in coming days. Thank you.